So welcome back, everyone, to part 3 of the tutorial. The goal for this last part is to sort of talk through the derivation of what is arguably the main theoretical results in the lever paper that Jason referenced in part 1, namely a characterization of lever in a natural Black-Scholes-style model. So I'm going to state that main result for you in the, I think, slide after this one. First, let me just remind you of a couple of things that you saw in part 1 and part 2. This is the definition of lever that Jason gave in part 1. And so back in part 1, we were kind of thinking, about taking lever to data. So we were thinking about kind of doing forensics. So imagine you had provided liquidity to an automated market maker, and there was a sequence of trades in the past, and you wanted to sort of assess what were the adverse selection costs you suffered on account of those particular trades, right? So we're looking at it for this definition on this slide. End trades, AIs, those correspond to the quantities. So the quantities that you're forced to sell of the risky asset. Here, PI denotes the sort of open market price. So think of that like on a centralized exchange. And here, QI is the price paid on the AMM. So you want to think of P as the current price and Q as a possibly stale price. So for example, if you were forced to sell at a stale price that was too low, so if the open market price PI is bigger than the price you were forced to sell at Q sub I, then that would be some positive lever that you would accumulate. That would be some adverse selection costs that you suffer on account of providing liquidity. Okay, so we're going to be referring back to this over and over again. The quantities, the AIs, times the sort of gap between what the price should have been had you done the trade on a centralized exchange versus the price you actually had to suffer given that it was done on an AMM. Okay, so I just want to have that fresh in your mind. This is the results that we're going to focus on in part 3, arguably the main result of the lever paper. Not everything here is defined yet, but what's missing we will fill in as these parts go along. So we are going to have a theorem about lever accumulation, but now rather than looking backward and asking what adverse selection costs did we suffer from a sequence of trades in the past, we're going to try to make predictions about the future, right? So if we're contemplating providing liquidity to an AMM, should we do it or not? Well, to do that, we need to have a forecast, not just of our revenue coming from fees, but also of the prices, right? Because the lever is going to depend on the prices. If the prices never move, there's not going to be any arbs, there's not going to be any lever. If the price is moving a lot, presumably there's potentially lots of arbitrage, which potentially means lots of lever, okay? And so as CMAC sort of mentioned, for this question, it's natural to pass actually to a continuous time model. So we're going to be thinking about prices kind of changing all the time, and there's going to be arbs all the time. And we're going to just watch how lever accumulates as time rolls on. And so this result is a characterization of that lever accumulation, right? And so you'll notice there's this integral, right, over this time interval from 0 to t. And again, prices are changing all the time. Arbs are happening all the time. So that's why we're integrating instantaneous lever. Little l is instantaneous lever. We're integrating that over the whole time interval. We're always accumulating more and more lever, okay? And then the formula for the instantaneous lever is given sort of lower on the slide, and it's this 1/2 times quantity sigma ps squared times what CMAC was calling the marginal liquidity. So this is the same x star, the same derivative of x star that CMAC talked about at length in part 2. And again, sigma is not yet defined. We will define it, but intuitively that's going to be the volatility of the risky asset. So how much the price we think is going to be jumping around in the future. So you see this. So first of all, I hope it seems like a very natural question you want to answer, right? What kind of lever should you be sort of predicting, going forward, and characterizing it in natural mathematical models? I don't know if this strikes you as a simple formula or not. It sort of depends on your prior, and I'm not sure what your prior is. Certainly by the end of part 3, I hope to convince you that this is actually about as simple as things could have possibly turned out. That we should be very pleased about how clean and simple this formula is. And in particular, we'll see exactly sort of where the terms in this instantaneous lever come from. But before we do any of that, before we talk about the derivation, and before we talk about the model, which we're going to do the derivation, which is going to be geometric Brownian motion, let's actually just instantiate this theorem for our favorite running example, which again, CMAC talked about at length in part 2, namely a constant product market maker. I see something popped up in the chat. That's great. So Jason said it at the beginning, but let me say it again. Please ask questions in the chat as I'm talking, and Jason or CMAC will sort of be responding to it. So if anything's unclear. There'll also be plenty of time for questions sort of at the end of the tutorial. Good. So constant product market maker. I just want to instantiate the theorem we just saw for a constant product market maker, and I want to figure out what the lever will be as a function of this, intuitive but not quite precisely defined volatility sigma. So this is just copy paste from one of CMAC's slides. Right, so he was talking about, let's not think about AMMs in terms of the sort of invariant function, little f, but let's instead think about them in terms of the demand curve. So fix the liquidity parameter capital L as a function of the current market price. That sort of uniquely tells you how much of the risky asset is going to be held in the pool after arbitrageurs have done their thing and corrected the spot price so that it matches the open market price. And some simple kind of calculus and algebra for the constant product curve tells you exactly what that demand curve looks like. Okay, so as CMAC said, it's going to be decreasing like 1/square root of the open market price. So capital L is the liquidity parameter, so that's the geometric mean of the quantities X and Y. And then the demand curve is just that liquidity parameter capital L over the square root of the price. Similarly, the pool value, remember this is just kind of the value in dollars of the combination of assets that are held in the pool. Right, as CMAC said, that's always sort of going to be a concave function, concave in the price of the risky asset. For the special case of a constant product market maker, that in fact is just 2 times L times square root of P. Okay, so those are both going to be relevant terms for us. Now let's sort of evaluate the formula we had a couple slides ago. And here I've sort of, again, showing you the instantaneous lever. Just hide that, okay. So let's just literally plug in and see what we get, okay? So in the instantaneous lever, right, we see that we have not just the demand curve X star, but the derivative of the demand curve. So that's what we're calling the marginal liquidity. So the demand curve is L over square root of P. So we take the derivative of that. What are we going to get? We're going to pick up a minus 1/2, and then the root P on the bottom is going to become a P to the 3/2. Okay. So this thing on the right, once you take the absolute value, that's going to be 1/2 capital L over P to the 3/2. We're multiplying that by a P squared. So that 1 over P to the 3/2 is going to become a square root of P. And then we're also going to pick up that sigma squared. So if we just plug in for the marginal liquidity, we get L times sigma squared over 4. Again, one of those 1/2 is from taking the derivative from the 1/2 in the exponent. The other 1/2 is the one that's sort of there staring at you in the face in the upper right. So L times sigma squared over 4 times square root of P. And again, that square root of P is because we had root P in the denominator, took the derivative, had P to the 3/2 in the denominator, and then had P squared on top. So that gives us the root P at the end of the day. Now let's express instantaneous lever as a function of the current pool value, as a function of V, right? V, as it says right there, 2 capital L times root P. So we can swap out that L root P, replace that by V of P, but then we lose another factor of 2. We get sigma squared over 8 times V of P. This is really, really, really nice. This is kind of quite remarkable property of the constant product market maker, that in some sense lever, at least lever normalized by the pool value, doesn't even depend on what the current price is. Doesn't depend on anything other than the volatility. It is always sigma squared over 8, okay? That is the percentage of the current pool value that you are losing to lever, to adverse selection costs. So if you just can plug in a value for sigma, so what would a typical value of sigma be? Like, well, for the daily volatility of ETH, for example, sigma might be something like 5%. And again, you plug that in, and then you are getting that you are losing 3 1/8 basis points daily due to lever, due to adverse selection costs. Okay. Is that a lot? Is that a little? Well, again, providing liquidity, it's this cost-benefit analysis. You got to compare your revenues to the costs. Lever is just isolating the cost part of the cost-benefit analysis. The fees, that's going to depend on the volume, right? So if this pool has like tons of action, tons of trading, then you're going to be fine with this amount of lever. You're going to be profitable. If the pool does not have a lot of volume, then in fact, your revenues might be swamped out by these adverse selection costs. Okay, so the benefit, you still have to make a sort of bet or a prediction about the volume, but this theory tells you exactly how to think about the cost. Okay. All right, so even if that formula didn't strike you as simple a couple slides ago, I hope you'll at least agree that once you instantiate it in sort of our favorite running example, it does become remarkably simple. Sigma squared over 8. All right, so let's now talk about why this theorem is true, and also just talk about the model in which it's true, right? Because again, if you're looking in the past, you can just use what the actual market prices were at those times. If you're trying to pick the future, you need to have a model of what the price trajectory is going to be. So let's talk about the derivation. And the plan, let's see if we can just kind of follow our nose, start from the discrete version of lever that Jason talked about, so this blue formula on top, and kind of almost by a sort of heuristic limiting argument, see where we get, okay? So we want to think about kind of these trades happening very frequently. And then we want to think about sort of the price changing, and we want to think about the lever incurred each time, okay? And one reason we're doing this is because you look at sort of what we already know and where we're going to, and they don't look crazy different, right? We have in the blue formula, we have this sum over trades. In the black formula, we have this integral over time. But remember, we're going to work in a model where there's sort of price changes all the time, and so arbs all the time. So that makes sense. The sum matches up with the integral. We've got these product of two terms in the blue formula. We've got a product of two terms in the black formula. Can we sort of match them up? And just so you know where we're going, the answer is going to be sort of yes. And so basically, the quantity term, so the AIs, that's going to sort of be dictated by the marginal liquidity. And also it's going to pick up one of the factors of sigma times P sub S. And then the gap in the prices between the price of the AMM trade and the open market price, that's going to pick up the other factor of sigma PS and the 1/2. Okay, so that's roughly, this is not a proof of anything, but this is just to sort of orient you, right? So in effect, the formula I stated in the theorem does correspond in a pretty direct way to the blue formula, to the formula for discrete lever that we had earlier. Okay, so that's the plan. All right, so this slide is going to be a really sort of important thought experiment for us. So let me go through it slowly. So again, we're going to think about the price changing all the time and arbs happening all the time. So let's use S to index time, and imagine just we fast forward the clock slightly. Okay, so we go ahead an infinitesimal amount ds in time. The price of the risky asset is also going to move. Okay, so it's going to move by some dp, all right, from the old price ps to a new price ps plus dp. So this price move, right, is an opportunity for an arbitrageur, right? So this is now, they can now do a trade on the AMM, and they can correct the spot price from the now stale price of PS to the newly current price of PS plus a DP, okay? And I want to understand what is going to be the lever that we suffer on account of this infinitesimal arb trade, okay? And so to understand sort of the cost, we need to understand both the quantity of the trade, how much gets traded, and we need to understand exactly how stale the price was. That corresponds to the product of the AI and the PI minus QI. Okay, we need to understand both of those two terms. Okay. Now, CMAC made a big deal about the marginal liquidity in part 2, and as he should have, that's going to play a very important role here. So again, remember the interpretation of marginal liquidity. This says that if you want to move the price of the AMM a little bit from where it is right now, how much do you have to trade? Okay, so remember CMAC had this sort of nice picture with these two prices sort of far apart, and he talked about the sort of rate at which you're trading as you pass through all of those prices. And that is exactly the picture I want you to have in your mind right now. Okay, so marginal liquidity, the rate at which you have to be trading in order to sort of affect the spot price of the AMM a little bit. Okay. Now, the marginal liquidity in general does depend on the current price, right? But we're just sort of working with infinitesimal trades. So to first order, we're just going to think of the marginal liquidity as constant, okay? It's fixed at where it was at the price PS. Now let's talk about how big is this arb trade going to be, and how stale at which the trade is executed. How stale is that price going to be? Okay, let's answer those one at a time. Let's start with the quantity. Okay. Well, how far is the arbitrageur trying to move the price? It's trying to move it from PS to PS plus DP. Okay, so it's trying to move it DP units. How much does it have to trade to move it DP units? Well, what did we say? We said marginal liquidity is the rate at which you have to trade to move the price. Okay, so it's the amount you need to, so the quantity is going to be the amount you need to move the price, DP, times the rate you need to trade at which to sort of move it, and that's the marginal liquidity. And so this is analogous to the AI in our blue formula. Okay, that is the quantity of this infinitesimal arb trade. How about the price? Okay, so we had this PI minus QI, right, in our blue formula. We know what PI is. PI is just the current correct price. So now in this context, that's PS plus DP. Okay, so PI in the blue formula corresponds to PS plus DP on this slide. So what is QI? QI is the price at which the AMM trade is actually executed. Okay, and that's a little bit trickier. Okay, because when the arb trade happens on this AMM, when it first happens, the first little bit of the arb trade, the AMM spot price is the old price, PS. When the arb trade concludes, the spot price will be corrected. It will be to the appropriate current value, PS plus DP, but it will pass through all spot prices in between PS and PS plus DP en route, okay, as it executes that trade. Exactly the same as in CMX figure, where you had the P naught and the P1 and talked about sort of trading and passing through the prices. Right, same thing here. Initially, spot price is PS, it eventually goes to PS plus DP. So the overall price of the trade, so like the average amounts paid per quantity, is going to be some mixture, some average of PS and PS plus DP. But actually, our life gets really simple here exactly because the marginal liquidity we're treating as constant for this sort of infinitesimal trade, right? So we are passing between all of these different prices, PS, concluding at PS plus DP, but we're trading at exactly the same rate the entire time, okay? So that means that the average price is just going to be, the average price paid per unit is just going to be the average of the starting and the ending price, the average of PS and PS plus DP, also known as PS plus DP over 2, okay? So now we understand what's the analog of AI and PI and QI from our blue formula, right? AI is the price change times the local marginal liquidity. PI is just the new price, or PS plus DP. And then QI is the midpoint between the new and the old price, okay? And so the lever, right, so the AI times PI minus QI, right, what's that's going to be? That's going to be the quantity, so DP times marginal liquidity, times the difference between the sort of open market price, PS plus DP, and the AMM price, PS plus 1/2 DP. So that difference is going to be 1/2 DP, so that picks up our second factor of DP, plus that's where we pick up the 1/2, okay? So this is a crucial thought experiment, right? So in continuous time moves a little bit, price moves a little bit. We can figure out what the lever suffered from the arb trade is. It's as a function, right, of the marginal liquidity. It's also a function, notice, of DP, right? So it depends on exactly sort of how much the price moved. That's going to be right. That's what sort of dictates what the lever suffered at this moment is. Okay. And this is starting to look promising, right? So if you remember what we promised you in the theorem, the instantaneous lever looked pretty similar to this, right? We promised that the instantaneous lever was 1/2, check, times the marginal liquidity, check, times quantity sigma PS squared. It's like, okay, we don't have that. We have a quantity DP squared, right? So what's remaining to do is sort of understand why does this DP squared becomes quantity sigma PS squared. And if you think about it, I mean, like, we better do some more stuff, right? Because we still have not actually committed to a model of how prices are going to evolve over time, right? And so what we have left to do is actually write down that model, which is going to be geometric Brownian motion. And in that model, it will in fact be the case that DP squared will be equal to quantity sigma PS squared. Okay. All right. So again, for any of this to make sense, right, we need to sort of have some distribution over price trajectories, right? We need to have some sort of forecast for how the price is going to move, okay? So what should that look like? How should we do that? You know, well, one thing you could do is just like look up in a finance textbook and copy paste whatever comes up in like chapter 1, and in some sense we will do that. Another thing you could do is kind of say like, well, what's like the simplest thing that would make sense given what we're trying to model? And we'll actually arrive at exactly the same place, which is Brownian motion. So what do we want? So what sort of property should this sort of distribution have? Well, the price should be locally unpredictable, right? So like if at some given moment in time, S, you know that the price is 100, you should have no idea what's going to happen next, whether it's going to go up, whether it's going to go down, right? If you could somehow know whether it's going to go up or whether it's going to go down, that's supposed to be reflected in the price, right? So the assumption here, it's kind of an efficient markets hypothesis. The price is supposed to reflect all of the available information, so you literally just have no idea what it's going to do next. It's very natural to assume, and we're going to assume also that it's Markovian, right? So if at time S, the price is 100, you do not care how it got to 100. You don't care if it went up and then back down, or down and then back up. All that matters as far as knowing what's going to happen in the future is that at time S, it's 100. Okay, that's what I mean by Markovian. So there's a lot of different stochastic processes, right, with these properties. For the EC audience that I have in mind, I would imagine that sort of the first thing that you would think about, or what you're most comfortable with these properties, would be like a random walk, or really just sort of coin flipping. So you could imagine just like you start with, a random variable equal to whatever, 0 or something else. And then you could imagine sort of, time proceeding in steps, right? So s equals 1, s equals 2, s equals 3, etc. And then each time step corresponds to a coin flip, basically. So the sequence is equally likely to go up or down. Let's say it goes either up by sigma or down by sigma. So sigma here is going to be the step size in this random walk, which sort of loosely is going to correspond to kind of the volatility in the end. Okay. So here's locally predictable. You don't know if it's going up or going down. And also, like as far as the future values of the sequence, all that matters is the current value. You don't really care how you got to the current value. So it's got this local unpredictability and also the Markovian properties. Now, if you're trying to price like a financial asset, like this obviously doesn't make sense, right? So like in particular, everything in the sequence is going to be a multiple of sigma, right? So it's like very discrete. Prices of, financial assets are, it would seem very continuous, right? So, okay, let's not do this quite this simple a random walk thing. Maybe instead of just adding sort of discrete things, we should add continuous things, right? So like if not sort of a coin flip, maybe we add sort of a Gaussian, right? That would seem to kind of best reflect what we're trying to do here. So for the moment, let's just still assume that like there are time steps. So if something happens at s equals 1, s equals 2, s equals 3, s equals 4. But now instead of flipping a coin, you just add a Gaussian, right? So let's say the Gaussian is mean 0. That's not super important, but let's say it's mean 0. Now let's say the standard deviation is sigma. Okay, so variance sigma squared. Okay, so just like with the coin flip, you're kind of expecting to move by sigma either way. It's sort of symmetric, up or down. You don't know which, but it's normally distributed. Okay, so that'd be the next idea. It's like, okay, now at least we can have like continuous prices. But even this is it's sort of like this doesn't seem good enough either, right? Because you're kind of like, well, what are these like time steps? Like, what are these like magical restricted times at which people are allowed to trade or prices are allowed to move, right? Prices are probably moving all the time. People are trading on exchanges all the time. So you probably want a continuous time model also. So in some sense, it still makes sense to kind of have this sort of like, Gaussian sort of increments, but somehow we want it to happen, we want it to sort of accumulate over time rather than just happen in these like batches, like each time step. So if you think about that for a little bit, and then you try to write down like what that would actually mean, I think the first thing most of you would write down would be something like this. It's like, okay, so we don't have distinguished time steps anymore. We're just going to have kind of a sequence, not a sequence. We're just going to have sort of random variables that are indexed by all non-negative reals, so all possible times s, not necessarily integers. We still want it to be the case that like, xs is the same thing as xs minus 1 plus kind of a Gaussian, with variance sigma squared. Same thing, like if it's 2 time steps later, the difference should be like, a Gaussian with variance 2 sigma squared. But we want that actually also to be true if s and r are not integers, or if the difference is not an integer, and if the difference potentially is even very small. Okay, this is what I mean by like sort of the Gaussianness should be sort of constantly accumulating. Okay, so formally, what does that mean? It just means that if you take, so you have this family of random variables indexed by s. If you take 2 of them, xs, xr, the difference between them should be distributed like a mean 0 Gaussian with the corresponding variance, meaning variance sigma squared times the length of the time interval between the 2 of them. Okay, so the basic variance sigma squared times s minus r. All right. So again, this matches the variance you're getting in the previous model with this sort of increments only once every time step, but now it's sort of defined also for, time intervals of all lengths, not just of integer lengths. Okay. And I guess, and then you also want the Markovian property. It should also be the case that sort of this sort of, the distribution of xs minus xr shouldn't depend on sort of what happened prior to r. Yeah. And I really think maybe you'd write that down, right? Just from this conversation, that actually is in fact Brownian motion. Okay. So if you were ever scared of Brownian motion, like don't be scared of it. It's in some sense like what you would think about if you wanted the simplest possible model that kind of made sense for pricing assets that sort of trade continually. Now, unlike sort of the simpler models where it's kind of obvious that they exist because we just define them constructively, right here, it's more like we're sort of defining this collection of random variables and we're defining a whole bunch of constraints about sort of, the distribution. So you actually have to prove that such a thing exists, but it does. And if you study, sort of, a course in this topic, that's probably one of the first things you'll learn. So we'll just take that on faith. All right. So again, this kind of seems like, what else would you do, right? But, once you have Brownian motion, and you start thinking about it a little bit, if you've never seen it before, you start realizing it has some properties that take a little getting used to. Okay, and there's one of those that's actually going to be extremely important for us. So the variance is the length of the time interval S minus R times sigma squared, right? And if S and R are like far apart, that seems like totally reasonable, or totally intuitive. But think about it when S and R are like really close to each other. So think about a time interval that has a really tiny length, epsilon, okay, really small. So that means, right, you actually expect the price to move in this interval by sigma times square root of epsilon, okay? And when epsilon is really small, right, square root of epsilon is really big compared to epsilon. So in this kind of really tiny time interval, you're actually expecting to see a kind of really massive deviation in the price. This is what I mean by kind of the local violence of Brownian motion. If you look at really small time intervals, it's really sort of wildly flailing all over the place, right? In particular, it's really not differentiable. You can see that immediately from this fact, okay? So saying this a different way, if you want to talk about sort of the change in price you're expecting infinitesimally, so dp, right? So that's going to be like sigma, the volatility, times the square root, okay, of the time interval, square root of ds, okay? So that's an important property of Brownian motion, which if you haven't seen it before, again, it's just worth kind of internalizing, okay? Really big price changes relative to the size, to the length of small intervals. All right, so if you think about it, Brownian motion also doesn't quite make sense for the pricing of financial assets, right? Like if you think about like stocks, right? If you have a stock where the share price is 1,000 and another stock where the share price is $10, right? The fluctuations are going to be different, right? Like you're probably not expecting to see the $10 stock become, $100, but you wouldn't be shocked to see the $1,000 stock become $1,090 at the end of the day. So actually what we generally want to use is not Brownian motion, but geometric Brownian motion, which just says it's basically everything is scaled by the current price. Okay, so there's different ways to think about it. One way to think about it is you're doing Brownian motion in the exponent of the price rather than on the price itself. Or you can just think about it that sort of variance is accumulating over time, not at like the constant rate of sigma squared like it was before, but rather with a price scaled sigma squared PS, okay? So this equation above looks a little bit different. That also gets sort of scaled now by P sub S, right? So rather than dP being sigma times square root of ds, dP is going to be sigma times PS times square root of PS. Okay, you're just sort of scaling the standard deviation linearly. And so now, okay, remember what we really cared about. I'll put it back on the slide, but pretty much we have all our ducks in a row now, right? So now we can look at sort of dP squared, so the square of the change in price. And we can see that that's going to be just the sort of length of the time interval in question, ds, times quantity sigma ps squared, okay? And this is going to be the missing link between the two different expressions that we saw a couple slides ago, okay? So connecting the dots. So this is what I just said, right? For geometric Brownian motion, right? Lever sort of accumulates sort of corresponding to the price change squared. And we now understand that for geometric Brownian motion, that's the same thing as the time interval length ds times quantity sigma ps squared. We did that thought experiment about what's the lever that accumulates from a single infinitesimal arb trade, right? So this was the one where we had sort of the analog of the AI, so the quantity, and then the analog of the PI minus QI, so the sort of price gap. Remember, if we want to move the price on the AMM by dP, we're going to be trading at a rate of the marginal liquidity. So that's where we get the dP times marginal liquidity. That's the quantity. Remember the sort of current correct price is the PS plus dP. And then remember that the trade on the AMM, because we have constant marginal liquidity, because we're trading at the constant rate between the stale price of PS and the correct price of PS plus dP, the average price of that trade is PS plus 1/2 dP. So that difference corresponding to PI minus QI, that difference is 1/2 dP. We took the product, we got the sort of adverse selection cost of a single infinitesimal arb trade, 1/2 times marginal liquidity times the price difference squared. We can now plug in that equation on top for price difference squared, and we get the instantaneous lever as claimed. Okay, so we get the 1/2. The dP squared now becomes our sigma PS quantity squared, and again, we have that marginal liquidity appearing there crucially. Okay, so here's just stating once again sort of that main result. Okay. So with a model of geometric Brownian motion for price evolution, you can get this, I think, as simple as you could hope for, characterization of exactly the rate at which lever accumulates. And also don't forget what we did at the beginning of part 3, where we evaluated this for constant product market makers. We got that sigma squared over 8. So this already, I think, is quite simple in general, but then it specializes to things that are even simpler for some of the most popular AMMs. So that wraps up part 3, and therefore sort of the tutorial, although all of us will stick around for questions if you have them. So just a couple of takeaways. So first of all, just the definition of lever, right? So we've known forever, it's always been kind of the price of business of doing market making, that you have adverse selection costs. That is not at all new to blockchains or decentralized finance, right? Traditional market makers worry about this all the time. It is somehow, I mean, it is somehow even more in your face, I would say, in DeFi on blockchains, because on-chain exchanges tend to update more slowly than other markets that are available, like centralized exchanges. And so that means there's always arbitrageurs with information that is sort of more current than what's reflected on the current spot price of an AMM. So as a liquidity provider in AMM, really, you're going to have average selection costs, even if nobody kind of is an insider trader or has insider information in the traditional sense of the word. Okay, so lever is really, really important, just as far as understanding how on-chain AMMs, like, whether they're viable. We saw in part 1, Jason talked about this. It's very easy to take it to data. I imagine there might be even sort of like MBA classes right now where students are kind of evaluating lever from data, in Excel spreadsheets. It's sort of basically as simple as kind of evaluating the volatility of an asset. It's kind of barely more complicated than that. On the mathematical side, we saw that in kind of a standard Black-Scholes-style model, that was this geometric Brownian motion model, you can actually characterize lever. You can actually get very crisp formulas for it for some of the most popular AMMs. And, the most obvious interpretation of this work is just this kind of guidance toward potential liquidity providers who are thinking about this cost-benefit analysis. Will the fees that I make from providing liquidity sort of exceed my average selection costs? I mean, again, you have to separately model the fees you expect to get, but this work tells you how you should model the average selection costs. And so then as an LP, you can sort of decide whether you want to provide liquidity or not. But also, if you think about it, sort of zooming out a little bit, right, this work also is helping to guide the design of the next generation of automated market makers, right? And I'm happy to see, we've been happy to see sort of many researchers thinking about this, many kind of startups sort of, trying to think about sort of new generations of AMMs. And in particular, right, to have a successful AMM, you need happy liquidity providers, right? And so all else being equal, liquidity providers want the lever to be as small as possible, right? So you like to have as little of sort of your value bleed out to arbitrageurs as possible. And so people are thinking about a lot of different ways of doing that, right? So two sort of, high-level approaches that, come up right away. One would be, it's like, well, look, lever depends on things like, for example, the volatility of an asset on a given day, right? So maybe you should have fees that also depend on some of the same things that lever depends on, right? So maybe, I don't know, if it's a day where it seems like things are really volatile, maybe the fees should go up to somehow protect the liquidity providers from sort of higher adverse selection costs. Another thing would just be like, can you somehow make the QIs better? So remember, the lever, it matters with this difference between the PI and the QI. Is there some way you can design your AMM so the QI is closer to PI than it would have been otherwise, and so the lever is lower? Maybe the most obvious way of doing this is incorporating external information, incorporating some kind of oracle. So maybe you have your current spot price QI, there's some oracle that gives you at least some kind of signal about what the real PI is, and maybe you can use that in some way to intelligently adjust your QI, hopefully in the direction of PI. So a lot of different things being explored. I think we're all very optimistic. There's going to be some cool designs that sort of keep lever pretty low for liquidity providers. Solving that problem may even be kind of essential for the long-term health of AMMs and sort of DeFi more generally. And that wraps up the tutorial. I think we're a little bit early, and all three of us are very happy to stick around for questions for any of you who have them. So thanks very much.